Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about Iron Man's suit. So let's dive right into it. Now first you have to understand, Iron Man is a very important character to me simply because it's one of my favorite. As in like all of the MCU characters, Iron Man is my man. Now fundamentally speaking, this movie fundamentally changed me in 2008. As in I was in school and I watched it in one giant projector screen, not as in like multiplex, as in like before the singleplex. So I watched in there and it was like mind-bogglingly changed because I still remember almost all the scenes of Iron Man 1. Like I don't even need to watch the movie. I'm like, you show me a scene, I'm like, oh, that's where the scene is. Like this is very influential to me simply because I love the fact that he builds the art creator, and the way the cinematography is done, it's like almost feels like you can do it. Like they show you the effort. It's like, oh, he's winding the coil, he has a gas tube, he has a this and that. It's like, I know it's all blah 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 props and dressing, but it feels so real. Like I was a kid back then and still am, but at that point in time I almost thought like I can do this. Like all I need is some copper wires and coils and all that. Like that was amazingly transformative to me. So like I changed, like started to think a bit differently. And they as a cinema system, as an ecosystem, they started very humble. That was the most amazing thing they did. They did not show the Iron Man as we have seen in like basically cartoon shows where it was like a complete briefcase system and almost like magic. But they started very grounded, as in this was very critical aspect, because if they directly showed you the suit they show in the final systems, people are like, dude, lol, that's not gonna happen. But they built it up. It's like, think of it this way: you go into 1990s, not 19, yeah, let's just go there, and directly show up someone a smartphone. We're like, what the hell is this? Now imagine showing them as a feature phone. Then you slowly build up. We had very big feature phones, that we had smaller feature phones, even smaller feature phone, feature phone with more option, feature phone with color screen, brick by brick you build it up, so then people can digest that. So I really love the fact that they went into the trouble of building something very low end, Mark 1, and then they started to brick by brick, going to a point where you can digest, like magical nanotechnology, where it's like tuk tuk, which please. So I love that. I really love that they went through that much effort. And then we come to another aspect. It is one of the few things, like when Star Wars happened, it was not just Star Wars happened, it was like a very big transformative thing, simply because there were projects that were made. Star Wars project, think of it that way. Like that amount of imagination was stirred, so to a point where people were like, hey, let's try to do this. You need that. Sometimes you need that imaginative push to like, hey, let me figure out how to do that. Because again, engineers are not very creative people. Artists are very creative, but artists can't do things. But if you combine them both, you're like, artist will design something, and engineer will like, let me see whether I can build that or not. So that's a very fulfilling system. You will see like things in 1970s TV shows or Star Trek. People are like, people started to try to build that, and we have successfully built it. Like tablets was shown in Star Treks and all that jazz, touchscreen and all that. Like that's common for us. So that happens. Like this is a common sin. Engineering will inspire imagination of artists will inspire the imagination of engineers, and that's gonna keep feeding back. So at this point in time, lot of country, lot of money, lot of corporations, lot of armies, they are pouring their money into it, trying to make this. Because now it's very easy to go to let's say your DARPA and be like, I need an Iron Man suit. So it gives collective imagination is now set on fire. Every Tom, Dick and Harry is trying to do this. Okay, now that's the movie aspect of it. Let's try to break it down as an engineering point of view, what you have to do in order to achieve Iron Man. Now this was when I saw this scene of Iron Man 1, Iron Man 2 doing this briefcase scene. Like I barely remember any scene of like old Fox Kids TV show where Iron Man actually had this kind of suit, and I still remember his faceplate was like always between his boots. That was amazing. So the idea behind this is a very powerful system, but it's very compact. You can have powerful tanks, but they're not small. Like think of this is like almost as powerful as a fighter jet, but small. It's like a freaking briefcase. Literally speaking, it's a literal briefcase. So that's the whole point. It's very powerful, but it's very compact. So the power density wise, this is like GG. Then we come to how it's all powered. Nuclear reactor. So it does not need to run on battery, it does not need to run on any sort of fuel. It has nuclear energy. That's how it can do all those things. Then that's the energy aspect of it. Then you have what does this whole thing, this thing that you see, the suit, what is it? This is basically what we call powered exoskeleton. on top of that, this powered exoskeleton has enough propulsion, enough technology, enough aerodynamics control that it can achieve supersonic flight, aka it can break the sound barrier. That fundamentally means you need GG amount of energy to achieve that. Like trying to hover, you can do that. Like people have successfully done that with drone motors and all that. Trying to go supersonic, yeah, lol. So this puppy can do that. And then it's a military system, so it has directed energy weapons, so you can do basically make things go boom very efficiently. So directed energy weapon, and on top of that, it is idiotically durable, as in you can see that, like I really like in Iron Man 1, they show like a fighter jet is there. Fighter jet is like the latest and greatest, and Iron Man suit is there, and Iron Man suit takes a lot of bullet hits and it can still survive. But when Iron Man crashes through the wing, fighter jet goes wing. And it happens, it's in real life, like fighter jets are not that durable. That's why we have proximity fuse to blow them up out of the sky. You have you send a missile as close as possible because it's moving very fast. Once you go close enough, proxy fuse is like go boom. So the shrapnel destroys the fighter craft. So it has armor. Basically, not only it can dish damage, it can take damage. So it's very robust system, and all that in compact system. So let's start with the most talked about topic, power, aka arc reactor. Now arc reactor is flat out magic. Let's not kid around. There is no something like this or that. No, lol, no, hell no, heck no. Arc reactor is just magic. Now again, think of an engineering point of view, what you need to do to achieve something similar as that. Well, first thing people will tell you is like, if you do nuclear reaction, radiation is gonna cook you. Well, that's absolutely true of fission, simply because not only the action itself creates a lot of radiation, the byproduct is even more radioactive. So fundamentally speaking, that's very quick way to die. So what can you do? Can you look into fusion? Yes, fusion does have the benefit, it does not create radioactive byproducts, but the reaction is still radioactive. As in, this is one thing that many people are not understanding, is like fusion still produces insanely high amount of neutron radiation. Neutron radiation can make other things so unstable that they will start to emit gamma rays to come down to lower energy states. So fundamentally speaking, you need something that is not releasing energy in a format that is devastating to biological life form, aka no radiation shall be allowed. So only option you have is a neutronic fusion. What does that mean? That simply means if the reaction is dumping, let's say 1 megawatt of energy, less than 1% of it would be in neutron form. Now there are many options, many fuel systems. Basically, you take a periodic table, you start with hydrogen, and you go down as low as basically carbon and iron. Before that, everything is fusible. So the best fuel I found is basically photon boron fusion system. I'm like, why the heck that? Not helium-3 or all that gas. It's basically, even helium-3 creates a secondary radiation where you're gonna be cooked alive. So yes, the primary system is not, but secondary radiation will be enough bad that you will be cooked to death instantaneously. So fundamentally, helium-3 no go. And not to mention, how the heck you're gonna find helium-3? It's like so expensive. It's only used in, like, quantum computer cooling systems. So you need something that in a cave can be done. So photon boron system. Now benefit of this puppy is has like all the options of basically a neutronic fusion. Proton boron has the least radiation output. Basically radiation output is almost raw zero, because you take a photon, you take a boron, and you go bang with them, it creates carbon, and the energy output is in alpha particles, aka very charged particle with very high energy. Benefit of that can be directly converted into electrical energy, directly one stage conversion. Like you have basically this boom event happening, the charged particle comes out, they interact with coil, induces charge into the coil, tada, electricity done, go home, sweet dreams. Like it can be done in one step. No, you don't need any basically giant steam power plant system. So something this small, in principle, in hypothetical world, it should be able to do this. So that's the whole point. It could achieve the point of low to no radiation, so Iron Man does not just die. So that can be done. And then we come to another aspect. How the heck Iron Man is alive when the suit is not connected to him? Like he has a chest reactor all the time. How the heck is not dead? Well, it needs deep throttle, aka let's say the reactor output is up to 1 megawatt. He cannot be running on 1 megawatt. He has to go down to, let's say, the chest magnet he needs to keep his heart alive. Let's say that consumes 50 watt of power. That's too high, but let's just go with that 50 watt of power. At good enough efficiency, you are talking about waste heat of around 20 to 30 watts. Even let's just go waste heat of 50 watts. Your body can manage that. You have to drink a lot of water. You're gonna sweat like there is no tomorrow, but you can manage that. And if you are in a colder climate, that might actually be nice. So that can be done, but you need deep throttle, as in the reactor power you have to go low, like very low, like from megawatts to like few watts. Like you have to do that. Without that, the end. Then we come to realistic aspect of it. Physics wise, it's like, yeah, physics is a go. Engineering, hell no, heck no, you can't do this. Now you have to understand that nuclear physics is kind of gone through a very bad publicity stunt, so regarding nuclear fusion, so people don't understand. It's like, hey, we have achieved fusion. No, we have not. Fusion requires few steps, so let's understand that step. Step 1, ignition. Child's play, we have been doing it from 1960s. Children can do that in their school. That's how easy it is. Break even, nobody at this point in time when I'm making this video, August 2021, has ever achieved it. That's the whole point. Meaning, we have giant national laser ignition facility or national ignition facility. It has huge ass laser. I mean, lasers that are the size of football fields. Huge ass laser, focusing light on a small point, creating confinement, compressing material to such a low, basically such a idiotically high density, it goes boom, as in actual fusion achieves. So I'm like, okay, then why don't we have fusion? Here's the deal. The laser took, let's say, 1 gigawatt of energy to trigger. The fusion output was less than 1 gigawatt in thermal energy. And assuming a realistic conversion inefficiencies, you need at least 2 times or 5 times the energy output. So you put 10 megawatt in, thermal energy output has to be like, 10 megawatt by, like, let's say 60 or 70 megawatt. Then you will have some way of converting it, going through all the losses. Then you will have a power plant capacity of, let's say, 30 megawatts. So that's the reality. We have not achieved breakeven at this point in time. Every system that you see is just igniter, is just at the ignition stage. That's the, then you can say, in principle it can be done, but we just have never managed to do it. All the ITER facilities, all the radiation systems, like we turned on the reactor for 50 seconds. Like, was it producing energy for 50 seconds? No, we have never achieved breakeven. Like, think of it this way, if the reactor time is tested in seconds, how the heck is it even a reactor? So that's the one thing, we have never achieved that. Now once you achieve that breakeven, then you have to worry about conversion. Now on paper, on principle, a direct energy conversion from an neutronic system should work, and people have built mock-ups of it, actual prototypes of it, and actual test from an actual fusion system. Again, not in energy positive system, but it was like more of a test of a system. It does work, but only the difference is the system that tested all this thing was the size of a giant building, not the small. Then we come to the energy density aspect of it. Like, there are many systems that have like giant reactors and all that. Just when you consider they're like 11 tons of coal, like, that's not dense enough. Like, we have boilers that drink 11 tons of coal, like, that's blah. So fundamentally, all these things fundamentally limit the engineering side. Can it be done? If you really want to stretch it, that's the only way you can achieve it. You have to have photon boron system, you have to have neutronic fusion, you have to have deep throttle, and then you have to have some way of connecting the thermal output once you connect to the main source, which can be done. So then we come to the magical suit aspect of it. Now, suit aspect, a lot of engineering companies are pouring their heart and soul into this, and that's why I specified having a good science fiction is really helpful for your country, because your country will start spending money on building the science fantasy into science reality. It has happened enough time that people know that it's important. And if you ever wondered how the heck US military invest money in Hollywood, that's one of the reasons. So many times exoskeleton is built on hydraulic system. Now hydraulic systems are powerful, but they are ludicrously clunky and bulky and non-precise, as in you go from this to this, you don't go. This is very difficult to do in hydraulics. This is very easy to do, and like force wise, that's hydraulics is like, bitch please, I got this. But in terms of precision, finesse, like basically Iron Man suit, like he can even dance in that suit. That's not gonna happen in hydraulic system. It's too bulky. And not to mention, you do not want to convert energy from format 1 to format B simply because it wastes a lot of it. So you want to go direct electrical energy from the reactor into electromagnetic based system. It could be linear accelerators, it could be a lot of small motors. Now fundamentally speaking, we have built this sort of system, and the primary limitation in all of them are energy. So either military is working on a like very powerful system. The problem they came up to is like, yeah, they built the system, it works, it was powerful enough, it can lift actual missile battery that needs to go onto basically aircrafts. They did that, everything was awesome, but they needed a giant cable coming from the main generator. So it can be the power source is the limitation. Right now the real world is limited by that reality, but assuming you have the power, you can do this, but you need a lot of small synchronous systems. Right now all the systems, they are very small. Now you're like, why the heck they are small? Simply because power to weight ratio of modern battery does not allow to go even bigger than this. Iron Man can go bigger on this, or even smaller. Like why the heck our muscle has such a high power to weight ratio? Like, think of how few grams our muscles is and how much power we can produce out of it. It's bonkers. But the sole reason is it works on a cellular level. Like every strand produces a little bit of force, then you combine enough strands, then you create enough bundles, then bundles creates a muscle, then you have GG amounts of power. So same can be happen if you have a lot of small motors, which you can even see in Iron Man 1 when the chest main plate is rotates like that, and you see a lot of small things rotating it. You can have a lot of small synchronous system, and then you can achieve the power density of Iron Man suit. Now this is one thing they did very well. The armor has a lot of overlapping. Basically, even here you have a giant shield here. Every place, like even this, every place has a lot of overlapping armor. And you may be like, why the heck soldiers don't wear that kind of armor? They can wear it. It's just they're gonna tire out and get heat stroke instantaneously. So fundamentally, and because of the power limitation, the exoskeleton can't do much. So this is like actual real world military exoskeleton. It's just like battery life is, I think, classified. So most people are assuming it's around barely 1 or 2 hours. So he has overlapping armor, so he can actually take hit from almost any side. And then we come to brutal aspect of it. That's why you need Jarvis. These sort of system requires very advanced computational system. You cannot operate them as like on a remote sort of system. It's like, oh, if my hand pushes on this transducer, it's gonna electric conducer, and then nah, it's not gonna work like that. It needs almost an intuition, because you don't think when you are moving your muscle. You don't go, I have to do like this. You just go. You don't think about it. That's a very critical aspect. You need very advanced AI, and this is one of the things that I liked about Halo universe. The suit itself is so advanced, and I'm like, dude, normal humans should die inside, and they said that in the, like, if they tested it on normal soldiers, they die instantaneously because they do not have the response time to react on it. So you need advanced AI, and then you need brain interface. Now you may like, Iron Man does not have anything going into his brain. Well, you don't need that anymore if you have good electrical detection system, which we have been building, we have been utilizing on a lot of amputees who have lost their limbs, and there are sensors on the muscle group. So muscle group, when it twitches, it creates an electrical impulse. Now that impulse would be very noisy. That's why you need AI to filter all that noise and figure that things out. It can be done that you can have a system that detecting your muscle movements, it can act on it, and AI that can be like, okay, no, you're imparting too much force. It won't just like, let's crush you inside. And it needs a lot of cooling for strength. Again, this is one of the things that in movies they don't show. It's like Iron Man just goes there. Here's the deal. If you stand that close to a normal jet engine, yeah, you cooked. Iron Man suit, he should instantly evaporate everything that is around it. It's like only way he can even work is like the conversion efficiency of thermal to propulsion is almost 100%, and then his total weight should be less than 200 kilos. So exoskeleton part is like a lot of people are actually working, and it's a really useful thing, not only for military but for firefighters, for people who have been paralyzed, or people who like old age people, which we have the side effect of living to almost 100 years, even though our muscles are like, bro, I can barely carry you. So this part is the most down to earth part, except the power part. So without power, this does not work. The only way you can do that is having a giant extension cord, which military did try to do that. Then we come to the magical aspect of it. So far, I can stretch belief. I can like, okay, he does this to do that, maybe. But the fly part, that's a magic. So far, I have not found anything that could even do that. So flat out, it's the main magic of Iron Man. He flies. Now, I do hate the fact that like now even Falcon has almost same suit capability as Iron Man. I'm like, dude, no. It's like people so nice. This was tiny jet engine without realizing jet engine drinks fuel like there is no tomorrow. You need giant tank to feed that. It's like, that's why Iron Man can work. Like you can't have like, normal thrusters that's like firing for a few minutes. It's like rocket burns through fuel in few seconds, and you have like this tiny thing that's producing enough thrust to move a giant human, and somehow it has enough fuel to do that for continuously. That can't be done. So only Iron Man should be able to fly that. I really hate that power scaling thing that they are doing now. Almost everybody is like Iron Man. I'm like, no. Unless you have a reactor that can produce that kind of power, you should not be able to do that. And then the magic is basically they take energy turned into propulsion somehow. Now you may be like, what about iron engines? Well, iron engine does require propellant, and this whole system is propellant free. Basically, Iron Man never needs propellant. You can even see that in Avengers movie where Thor strikes him with a basically lightning. Lightning is energy, and then he says power reserve to 108%, I think, or 180%, and he goes boom. Basically, he dumps energy into a physical format that physically moves something. That's the magical aspect. Basically, this magic, not the reactor. Reactor, I can buy that. It's pushing it, but it can be done. Exoskeleton, difficult, but it should be doable. The repulsor, yeah, that's something that I have not found anything that even comes close to basically describing. The only way I can even think about it is photons. Now, like, can photon physically push something? Absolutely. But if you were like, hey, didn't we already try to do this with photon cells, and like, it requires to work in almost vacuum? Yes, that's the problem. It does produce thrust, but it's so weak, so little. You need gigawatts of electrical energy, and God knows what kind of illumination LEDs you are using that is that efficient, and the light that will be produced would be brighter than the sun. No, not sun as a whole, the sun that we see. That the sink in, because you can see that many times when we have asteroid, especially in that Russian system, it was a day, but asteroid still casted shadow during daytime. How the heck it was that bright? It was not that bright because the sun is so far away that, like, it relative scale, it was brighter, and Iron Man should be even brighter than that. So from if Iron Man tries to fly, everybody into 100 kilometers of radius will be blinded or cooked. So photons, yes, it can do that. It's just so much photon. So fundamentally that's can't be done. And like in comics, he has muon system, which again, what the hell muon has to do with anything? It can be produced in particle accelerator, which you can't have in giant tiny palms. There, no, you can't have particle accelerator. Particle accelerators are only efficient if they are huge, so that not happening. And even if you are creating particles that are very powerful and you are directly creating it from energy, it still creates an issue. That particle will simply go through everything. It's like, yeah, it's just a heavier version of photons. It's like radiation. It's not. So as far as I know, I have not found any way of doing this magic aspect. Everything else I can explain, especially the reactor part. Is like, okay, a neutronic boron photon system with a good enough deep throttle, it should be doable. It's just everything else after that is like exoskeleton. People are working on it, people are actually making it, and I can see that, like, at this point in time, you give military, okay, this battery bank is 10 times more energy dense, they're like, okay, Iron Man, shoot, go, done, take it and go. So fundamentally it can be done. But this part I have not found a single way of doing it. So this was my presentation on basically Iron Man, sir. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.